Thank you. I was asked to give an update for CSCS and then make some advertisement of the next HPC User Forum meeting in Lugano, as you heard from Steve earlier this morning. In order to know what I'm updating on, I'm giving you an updated background. That's what I'm starting. Something that is often confused is exactly what is CSCS and where is CSCS located. So in Switzerland we have something like the Office of Science, which is a bunch of national labs. I have here the acronym. So Paul Scherrer Institute is would be the lab that collects the equivalent of APS, ALS, the SLAC and SNS of the US in one lab. So a spallation source, free electron laser, and a very modern light source that, like APS here, keeps being upgraded. And then a number of other labs, a material science lab and environmental labs in Switzerland. And the difference maybe to Office of Science is that we have two of the top schools, engineering schools, that are part of the same system. And ETH Zurich is the one I'm associated with. And ETH Zurich then has a number of outposts. So it's the main thing is the school in Zurich, but then it has an outpost in Basel, in the northwest of Switzerland, and another one in the south of Switzerland, and that's CSCS and the Swiss National Supercomputing Center. In fact, it has a fourth outpost, which is Future Cities Lab in Singapore. The center itself was founded in 1991, so more than 25 years ago, is located in Lugano, and I've seen talks where the center, the compute center in the US with the nicest view is NERSC. In Berkeley, you should come to Lugano to see what we have to offer on that side. We have about, we're going up to about 120 staff. This started at about 10 years ago when I took over, so the organization is growing and continues to grow. So this number could go up to 150 in a few years from now. Very international, as most things are in Switzerland. When you are in a small country, you're depending on immigration, and we've grown to power and cooling performance of about 12 megawatts upgradable. One thing I can say, and I will repeat it in this talk, we are not going to 40 megawatts in Switzerland or to 100 megawatts. This is something we will do elsewhere. The key mission is to develop and operate supercomputing capabilities required to solve important problems in science and society. And I hope to give you a flavor of what we mean by this. We support at any time always about 2,000 active users in about 200 projects. So that's the number that seems to stay about stable. Our main program is the High Performance Computing and Networking Initiative that is funding a user lab. This is a research infrastructure. I mentioned the light sources and spallation source, and so the computing infrastructure is considered to be one more of these research infrastructures, very similar to the OLCF or ALCF in the DOE framework. It is not a programmatic compute resource like NERSC. So everything we are offering is offered in an international context. The user profile is very similar probably to any supercomputing center with physics, chemistry, material science, environmental science, etc. And the question then is always, which one is your biggest community? And there my counter question is, do you consider allocated node hours or allocated storage? And that depends. So environmental science is relatively small as of now from allocated node hours, but on the data and storage side, they are one of the biggest. As I mentioned, we are a research infrastructure, and as such, the tradition in Switzerland is to be open and international. If you want to lead in science, you should not have national borders, and I guess that's true for all countries that lead in science. So we are a member of PRACE, which is the European Partnership for Advanced Computing that offers tier 0 allocations, and this is similar to the INSIDE program. You can see about a third, we're targeting about 40% of the system should be used for very large allocations, and the rest are more or less what we call tier 1 allocations, so they can be anywhere from 100,000 to below 1 million node hours, and tier 0 would be above 1 million node hours. There is, even in the smaller allocations, a fair amount of international participation. Inside PRACE tier 0, of course, there is also Swiss participation, so overall we're around 20 to 30% international usage. The flagship from a computing perspective has been Stein, which was installed in 2012, was one of the first Cray XE systems. Actually, I think the first that had more than 4 cabinets, and Cray at the time would not sell us a 12-cabinet system. We bought 3 4-cabinet systems and then worked together in collaboration to put it all together. And in 2013, so a year after Jaguar, this system was scaled out with GPUs for the first time, and then upgraded in 2016. And so it's been in a very large GPU infrastructure since since 7 years, 6 or 7 years now. And I'm asking the question today, at the time when we introduced Stein and scaled out with GPUs, the conviction was still, and at Cray, that Jaguar was going to be a one-off system, and GPUs have no future in HPC. And I had to fight very hard to convince people that this is going to be a different story, and that we should keep investing in this technology. And now we know that things turned out differently. So it was a good investment. But we still maintain also a relatively large partition of dual socket multi-core nodes. And so very similar to NERSC, this is a heterogeneous system with multi-core nodes and accelerated GPU nodes. Yes. So what, and this serves the user lab. But in addition to the user lab, it serves a bunch of other infrastructure. So I can't show you a slide with 5 or 10 different systems at CSCS. Of course, we have a number of small test systems. But we've gone to one very large infrastructure that serves a lot of purposes. The user lab is the biggest one, but we have a number of university clusters that have been moved into Stein. Then we have a number of large projects like the Human Brain projects and NCCR Marvel that are, one is material science and Human Brain project is neuroscience. I'm sure you've heard about that one. And we're running a platform on top of our infrastructure that serves these 2 communities. And CHIP is the Swiss Institute for Particle Physics. And this is very interesting. We used to run a tier 2 system at CSCS and then tier 3 systems at universities across the country, and that used to be the grid for the LHC data analysis. And the middleware, the grid middleware that Switzerland has been running has been moved to the Cray platform. And since 2017, the users of the Swiss grid did not know anymore whether they were running on a cluster or on the Stein supercomputer. And today, they run only on the Stein supercomputer. So the grid is absorbed into this infrastructure. And who would have thought, 20 years ago when the grid ideas came about and HPC was going to die out. And of course, we have a number of other exploratory projects. So now this is where we are today, and where do we go in the future? What I think the one mistake I made when going after Stein, this was driven by application needs, driven by very large investments that we made in applications. But we were never really clear about what the goal was, other than building a large infrastructure for users. And the big disappointments was, in my opinion, is that the media took note of this system basically just in terms of its position on the top 500 list, which for me goes, I'm a physicist and a scientist, is somehow kind of odd that we are ranking systems based on a rather irrelevant benchmark, or a number of irrelevant benchmarks. And since I have one more project of this scale that I can run before I'm forced to retire in Switzerland, I thought we need to do this differently the next time. So we set very clear, ambitious goal for the successor of Stein. And the goals are twofold. One is, we will build a general purpose supercomputer, to make that clear, so it will serve all domains that we serve today. But the performance goal is set to run what we call exascale weather and climate simulations by 2022. And the specific goal is we want to run a global model with a 1 kilometer horizontal resolution at 1 simulated year per day throughput. And the system should not have a footprint in energy or size that is much bigger than Stein. So that's the challenge on the performance part. And on the functional side, you've seen that we have today already, we are running one infrastructure for a number of services. Now this works very well, but has one problem. And the problem is, all the different customers have to look like nails, because we have one big hammer, which is a big supercomputer with a queuing system. And in the future, we would like to run different clusters on the same infrastructures, but tailored to the different customers. So we have to move towards a converged cloud and HPC infrastructure. And that's what we are doing. I will now talk about the first goal, this so-called exascale goal, although it has, the word exa in there, I would say, is rather arbitrary. It's just the same time frame like when you build the exaflop systems in the US DOE. The second part, the functional part, I will be talking about in a few weeks at the HPC User Forum in Lugano. So if you're interested in that and what we are doing there, then please come to Lugano. So you can ask why weather and climate? And there's a number of things that I can say there also, maybe over a beer or a glass of wine. I'm convinced that this is the mother of the HPC, of HPC in general. And I'm saying this as a material scientist who's been criticizing this field in the past. But I've had a chance over the last 10 years to work with this community, because this is the one thing that we may be less known for in public, but is probably the most important system we have. Because and it's less known because it probably doesn't show up on the top 500 list. We are running the simulation system designing and running the simulation system for the Swiss Meteorological Service. And this system, since 3 years, is running on GPUs, the model that MeteoSwiss is running in operation. So in 2015, we introduced the GPU-based system and for the Meteorological Service, and then half a year to a year later, they took it in operations for weather forecasting. And they are in a not global model, but in a regional model, running their model at 1 kilometer horizontal resolution. So we have quite a bit of experience, at least over the Alpine region, with running models at that resolution. And in 2016, our implementation of this model was about 10 times more efficient compared to the implementation that other weather services were using, including the German Weather Service. I put 2016 because that was the gap between CPUs at the time, Haswell, and the K80 GPUs. The gap would be bigger today with Pascal or Volta because HBM was introduced on the GPU side. Now, why did we do this at the time, move to GPU? So this was not a stunt, but it was the result of a co-design effort that was necessary to accommodate the needs of MeteoSwiss. What they wanted is to improve the resolution of their model by going from 2 to 1 kilometer. And this required a factor 10 increase in performance. They wanted to introduce at 2 kilometer resolution an ensemble, which ended up being another factor 24. And they had to improve their data assimilation. So overall, their requirements grew by a factor 40, and of course their budget didn't grow. The investment budget and operational budget had to stay within the same envelope. And the challenge was this factor 40 had to be delivered in a 3-year time frame. So the last system we bought for them was in 2012, and we had to introduce the next one in 2015 to be ready in 2016 for operations. And how do you overcome this factor 40? Well, one thing we had going for us is we had already made significant investments in the development of Stein and development of the community software. Cosmo is also used by our climate researchers, and we had moved the implementation from a monolithic Fortran code to a refactored Fortran/C++ code. So what we've done then, this was around 2010, 2011, we started, is what you see now also happening in E3SM in getting ready for exascale. The dynamical core was rewritten in C++ with a proper library and software, modular software structure. And the important part here was that the enable co-design is that we had a stencil library that managed the grid that had a backend for x86 and CUDA at the time, and so we could make, based on price performance, a decision whether we build a system with GPUs or CPUs. We even had a backend for Xeon Phi, and this was a different backend than the x86 backend, obviously, but both using OpenMP. And now we are also moving towards ROCm and the AMD GPUs. So, and it was this software refactoring that really allowed then the co-design of the hardware and introducing the GPU system. And once you have this flexibility with your software, I would say this is probably one of the truly performance portable codes that we have today. Not just portable, but performance portable across multiple architectures. And when you have a performance portable code, you can also ask the question, you know, how does it do on different architectures, etc. And particularly you can ask the question, how did we overcome the factor 40 and what can we learn from this? So this is when we compare the new code, new implementation to the standard implementation, and you can see we get about a factor 2 from that. Then when you've rewritten the code, you can tweak everything you have on the mathematical side without making fundamental changes to the algorithms, but you can clean up a lot of things. And that turned out to be a factor 3. The switch from CPU to GPU was only at a factor 2. This was before HBM. So today with HBM, we would probably have a bigger factor. Then we had a little bit of help from Moore's law still at the time, which, and here I mean really the same price, you know, same number of more performance, but at the same price. And we even could afford to add additional processors. Now this would make you nervous on the operational side, but it turns out because the GPUs are efficient from a power perspective or energy efficient, they actually reduced the power bill. So operationally the system became cheaper in terms of power bill, and we could invest the money into the people who have to support the new software. But the main message we take out of this, and I think this is true for anything in computational science, at least anything I've seen, there is no silver bullet. If you want to improve performance, you have to work on all parts. You can't change one thing and make everything just go a factor 10 or 100 faster. So it's a lot of work. Now, this is one reason we go into this area, weather and climate, because we do have a lot of experience there, and we want to scale this up now. The other reason are actually societal reasons. What you have here is the European, or actually all the models that exist out there or are used, global models for weather forecasting, in comparison in this graph here, yeah, you don't really see probably the laser pointer, is the forecast lead, the error, the mean error of the forecast depending on the lead in number of hours. And what you can see is in all cases the error in the uncertainty also increases, because we are talking about the chaotic system. But there is one model that stands out, and this is IFS from the European Center for Mid-Range Weather Forecasting. And so we are working with IFS. This will be one of the models that we are moving to exascale with ECMWF, and IFS will be one of the models we're moving to exascale. But even they are saying that they are far away from what they would need. It may be the best today, but we are far away from what we will need in probably 5 to 10 or 15 years. And the reason has to do with one of the big challenges that I hear from my colleagues in atmospheric science is the way convective cloud systems are treated. So there are a lot of subgrid parametrizations that are needed in these climate models, some of which are physically rather well justified. And interestingly, the convective clouds are not justified in a good way, and lead to one of the biggest errors that in the models, and then allows our great president, he can then pick the model that does what he wants to see coming out. So this is a really serious problem that needs to be removed, and there seems to be some sort of a coincidence or a chance that exascale can actually remove this uncertainty or bias in the models. And the way I can show this with data from a colleague, Christoph Scher, When you look, there's two ways you can look at these clouds. One is can you describe them in a simulation, one cloud at a time, or have the full structure of the cloud, or can you describe them at least in an average way, that the cloud coverage is described properly. And it turns out, so what we will see on the left is really try to see how are we doing with the structure of the cloud and how is this converging. And what we call bulk convergence is really the average or the first moment of the distribution. And it turns out, while with the structure of the cloud, we have no chance at converging at 1 kilometer and probably even 100 meters. We probably have to go down to a few meters. And so that's really very, very far away from what we can do computationally. But it turns out for the bulk statistics, there we seem to have a convergence around 2 or 1 kilometer, as these results on the right side show. And so there is a promise that investing in these simulations to go to this 1 kilometer resolution is not just increasing the performance and making incremental progress in the models, but it's really an expectation that this will make a transformation in modeling of weather forecasting, like the introduction of numerical weather prediction in the 1960s was a game changer in weather forecasting. Okay, so this, I think, is enough motivation to think about this problem seriously. Now let's look at the roadmaps and where we are with this community. Okay, I have to speed up, I see. This was going the other way around. So this is the roadmap of ECMWF, that you see the past and where they are predicting to go in the future. And what we are talking about with our effort is to pull in their 1 kilometer goal from the early to mid-30s by 10 years. And there is a value that you can associate with that, and that value is very, very big. You have to start, when you now engineer such a system, you have to say, what is the goal? Where are we going? And so we've tried to describe this in a more quantitative way. I'm skipping the details here. And then we went in and tried to assess where we are. And we do this with Cosmo, blowing it up to a global model. And we did it also with IFS. So both of these models ran on Stein at the full scale of about 5,000 GPUs and 5,000 CPUs. And then we can go through this, these individual goals and calculate the shortfalls. And what you see here summarized is that Cosmo, an implementation, a refactored implementation, is about the factor 100 away, IFS about the factor 250 away. So that's the performance gap we have to overcome. And in the case of Cosmo, where we've done a lot of analysis, and I have to go through this now very quickly. I will show you the paper where this can be read, but the main point is, the main message of this analysis based on memory use efficiency is that the code implementation is very efficient, but the implementation of how the memory is used, so the drivers and how non-stride 1 arrays are accessed in the memory is inefficient, and that there is basically a factor 2 that we can get out of that. And then we can go through, for the case of Cosmo, what are the things that we can do to overcome the factor 100. One is to replace the grid from a lat-long grid to a homogeneous grid. That will give us a factor 4. The bandwidth problem, a factor 2. Then there is a strong scaling potential that we have. So if the GPUs become more powerful, have more threads on the GPU, we can exploit that. Gives us a factor 3. And we're left with a factor 4 that needs to be overcome by other means. So a factor 25 is there with just work, and the factor 4 will require creativity. But the bottom line is, with the right investment and the right focus, this goal of 1 kilometer resolution can be achieved by the early 20s on the footprint of Stein. Quickly, if I may, this is really my last slide. The performance development should not stop there. We need two things. One is we need to further improve the performance to 5 simulated years per day. And you can say, well, if the codes are optimal, everything is optimal, you don't have Moore's law, what do you do? Now, it turns out that, and I will argue this, and we can discuss this in the break also, that the change in architecture might have a chance at doing this, because we are, when we talk about we are optimal for a given architecture, which is the current control flow architecture with given caches and so on. If we change an architecture to a place where we even further reduce the needed memory accesses, then we have a way to overcome potentially this factor 5, or at least a factor 2 to 3. The place where we will be out of luck is really with the needed reduction in footprint if we want to run ensembles. So I've been talking about one trajectory, we want to run an ensemble. And the alternative I see there is, because I'm not assuming we have Moore's law, quantum will not help us here, that we will have to scale up the data centers and go somewhere else. And in Europe, we have a potential. This is part of a collaboration with we have with other countries in Europe, and a data center in Finland that has about 200 megawatt installed capacity today. And I think that's where HPC eventually is going. So I'm convinced that this problem of weather and climate is really going to continue to consume us, and will lead the way to further growth in HPC, because there is an economic case, macroeconomic case, why we need to do this. And so I don't believe the story for extreme scale computing ends with exascale or exaflop scale computing. These are the collaborators I would like to acknowledge, and thank you.
Okay, maybe we have time for one question while Andrew gets set up here.
I'd like to cheat. Thank you, Thomas. 2 questions buried. Have you applied SDFG to Cosmo? And the second question is, what is the possible role of FPGAs instead of some of the other accelerator capabilities?
The first question I didn't fully understand.
Dr. Höfler's stateless directed multifunction graphs. Has that technique been applied to Cosmo?
Okay. The answer is yes. We are working with Thorsten on this, and the two things together. So Thorsten's work will probably not help us much on GPUs, but is targeted to FPGAs or coarse-grained reconfigurable arrays. And I think, so that's the hidden message that I had in that other slide looking into the future. I think the combination of course, a new architecture with an appropriate programming model, and that's really the direction, one of the directions we're looking at, and we put high hopes in. So the story will not end at GPUs either, I think. That's